SCR. Now, once again, look at current bus through the reactance XT. Terminal voltage is V and generated voltage is E. Now, power transmission or power transfer is equal to EV by XT sine delta. Let us consider the power triangles. Power angle equals, so this is the half sine waves, and delta versus PE, and at maximum point, P max is equal to, or PE max is equal to EV by XD, and EV into 1 by XD. 1 by XD is nothing but SCR. Now, when SCR is low, naturally P max also very low. Therefore, the second curve low SCR, margin is very low. When the margin is very low, the maximum power transfer or the maximum power transfer is equal to, our steady state stability limit is equal to EV by XD, which has been reduced, and hence dynamic as well as transient stability have been decreased. So in another sense, you can say that stability is decreased or stability margins have been reduced. Well, how it is possible? So let us take a power triangle, and this is the delta x-axis, P y-axis, PE, and here so this is the PM, mechanical power input. So generator is connected to infinite bus V and E. When fault occurs at the terminals, three-phase fault. So immediately after occurrence of the fault, what happens? So it fall down to, so this is delta naught, initial value. So after fault occurs, what happens? The accelerating area A1 and the decelerating area A2, this is A2. When the power triangle have been decreased to a lower value, naturally this is the available margin A1. So in the equilibrium criteria, A1 equal to A2, then you can ensure the transient stability provided this is delta Cc. Delta C less than or equal to delta Cc, the system is stable. The system is stable, right? So therefore, when the power triangles have been decreased, the available margins are also decreased. Sometimes it may lose the synchronism. It may lose the synchronism. And hence it is very important that low SCR leads to decrease in stability. That is very first point. Low SCR. Now, let us consider SCR equal to 1 by XD. SCR is low means XD is high. So therefore, voltage drop I into XD. Anyhow, IR drop is very negligible compared to IXD drop, and hence IXD drop have been increased. IA into XD drop have been increased. When the voltage drop is increased, naturally voltage regulation have been have been increased. This is the second point. second point of the SCR, low SCR. Okay. That means when the load on the generator, suppose this is the generator, this is the load. So this is IA. When the load on the generator has been increased, naturally the voltage will fall down. Voltage will be decreased. So if you want to maintain the same voltage, the burden on excitation system is more for maintaining constant voltage. Constant voltage against load variations. This is the second important point of the low SCR. Okay. So coming to third point, low SCR. SCR is low, that is 1 by XT. XT is high. When XT is high, suppose generator is feeding the load. So this is the load. This is the current I. This is generator voltage E and V. When fault occurs at a particular bus, what happens? The fault current is flowing through the circuit. So this is the E, XT. This is the fault, three-phase fault. This is the short circuit current. Now, short circuit current is limited by XD. So therefore, short circuit current will be decreased due to low SCR. This is the advantage. Due to increased reactance XD, the fault current will be limited, decreased. That is the advantage of the. So this is the third point of your low SCR. ISC have been decreased. Therefore, short circuit MVA can also be decreased. This is the low value of SCR. Next, coming to the high value SCR. High value of SCR equal to 1 by XT. Therefore, XT is decreased. XD will be low. XD will be low. When XT is low, very first one, so So synchronous machine, so XD, so this is the bus voltage V, E, this is the current I. The PE equal to EV by XD sin delta. This is the power transfer by the machine to the infinite bus. So therefore, if you want to draw the power triangle delta versus PE, you have power triangle. This is the power triangle. This is the normal power triangle. Maximum value is EV by XD. Now, when the SCR is increased naturally, this is high SCR, since low XD. So, and hence you have the power transfer capability is higher. Therefore, steady state stability limit have been increased. When the steady state stability limit have been increased, naturally it leads to, so this is the PM, this is the point. So initially it was accelerating area A1, decelerating area A2, and this is the A1 available margin A1. So compared to the first one, it may be very low. This is A2. A2 will be higher. Dynamic as well as transient stability have been increased. Stability margins have been improved. Stability margins have been improved with the highest here. This is the very first point. Do you have any questions in that? This is SCR is high, 1 by XT, XT is low when it is high. XT is low. When XT is low, IA XD drop is low. Anyhow, IARA drop is neglected. Very small, it can be neglected. So therefore, voltage regulation equal to voltage regulation directly proportional to IAXT drop. When the drop is low, voltage regulation have been decreased. It is low. Voltage regulation is low. And hence the burden on the to maintain second point high SCR to maintain constant voltage against load variations constant voltage against load variations, the burden on the excitation system is very low compared to the previous one. Very low compared to the previous case, that is low SCR. So that is the second point. Coming to the third point, point 3, high SCR. Here the generator is feeding the load. This is XD, E and V. When three-phase fault occurs at the bus, what happens? Very simple. The generator, this is E, and reactance is XD, and the short circuit occurs here. This is ISC. So when high SCR, this is low, therefore ISC will be increased, and hence fault current ISA have been increased, thereby MVA short circuit have been increased. So this is the disadvantage of the high SCR compared to the previous case. So this is the third point. This is the third point. Okay, have you understood or any questions? So coming to the size and cost of the machine, cost of machine. For the better understanding, let us assume that air gap length is doubled. So let us consider air gap. This is the cylindrical type rotor which has slots on the periphery, and in which you place the winding, armature winding, and so this is the stator. Normally air gap we have LG is air gap, LG1 is air gap 1. So when it is doubled, naturally you have stator. Now the LG somewhere LG2. This is the rotor, stator, rotor and stator. I'm drawing roughly. So to understand this concept, this is good enough. So now LG2 is 2 times LG1, gap 1. 2 times gap 1. When the air gap is doubled, what happens? So the mutual inductance LAD is the mutual inductance. Is proportional to 1 by XD, direct axis reactance. LAD is proportional to 1 by XD. LAD is the mutual inductance between A and D. So, therefore, the reluctance of the air gap length is also doubled. Here, reluctance proportional to gap Lg. Therefore, when Lg is doubled, R2 is 2 times R1. Reluctance of the case 1. The reluctance Therefore, the magnetic flux linkages becomes half of the previous value. Why? Because reluctance is nothing but, suppose reluctance is doubled, that means the permeance become half. P2 equal to half of the P1. Half of the P1. Permeance will become half. The magnetic flux linkage is proportional to permeance. Above the psi1. So the flux linkages are proportional to permeance. Therefore, flux linkages psi2 is half of the psi1. Half of the psi1, right? Therefore, the mutual inductance depends on LAD 2 equal to half of the LAD 1. It will become half. Therefore, to maintain the same open circuit voltage, the field current has to be doubled. IFD2 must be equal to 2 times IFD1. Because of these reasons, the field current must be doubled. Okay, that is the first point. Coming to the second point, when LG2 is doubled, the mutual inductance LAD and self-inductance LAA are equally affected. Therefore, the field current required to circulate the rated armature current IFD to circulate a rated armature current remains the same. This is the second point. So these two are important points. The first one, the field current required to maintain the same armature current is same, whereas to maintain the same voltage, open circuited voltage, the field current will be doubled. These two are the important points. So what is the SCR? So let us define the SCR. SCR equal to field current required and no load to generate the open circuit voltage rated excitation voltage generated voltage open circuit. The field current required to generate the rated short circuit current. So therefore, very first one is no load voltage. It is doubled and field current is same. Therefore, SCR2 is 2 times the SCR1. So denominator is same. SCR1 equal to IF no load 1 by IF SC1. Okay. Next one. Similarly, SCR2 equal to IFNL2 by IFSC2. Now this is equal to 2 into IFNL1 by IFSC1. IFS since IFSC1 equal to IFSC2, and hence it is equal to 2 into SCR1. Therefore, SCR2 equal to 2 into SCR1. This is the conclusion. So, the SCR will become double the previous value. SCR is doubled. Therefore, it requires the greater cross-sectional area of the field winding and hence the greater field copper wire. So, it increases field copper and it requires greater cross-sectional area. Greater cross-sectional area. And hence field pole size have been increased. Subsequently, the machine diameter also increases. The dia increases. Therefore, size have been increased, cost have been increased. Cost have been increased. Therefore, higher the SCR, size and cost have been increased. In modern days, people are preferring low SCRs. To reduce the cost of the machine. And to improve the machine performance, they are depending upon other parameters like FACS controllers or stability improvement techniques. Stability improvement techniques. This is the greater insight of short circuit ratio of the synchronous machine. It is very important and crucial of this subject. Now, if you have any questions, please raise your questions.